Hello and welcome to our lesson on higher derivatives and concavity. So a higher derivative just means we're finding the derivative of a derivative. Sometimes we also refer to them as higher order derivatives, but that's the concept, derivatives of derivatives. And there are a few places we can apply the use of higher order or higher derivatives, which we will see in just a few minutes. But let's start with the notation. If we're looking at f prime of x, that's our standard first derivative. Then f double prime of x would be the second derivative, so you would take the derivative of the first derivative. Or f triple prime of x would be the third derivative, so that'd be the derivative of the second derivative. And then after the third derivative, we usually just use the number here instead of the primes. So the fourth derivative we'd use a 4, the fifth we'd use a 5, the sixth we'd use a 6, and then the nth and so on, that would continue. But notice that that 4 is in parentheses because if our function, let's say it was called y, I don't want to put y to the fourth like this where it looks like an exponent. We keep the 4 in the parentheses that says find the fourth derivative of y. Okay? Now just remember what we're doing when we're finding derivatives is we're finding slope. So when we find our first derivative, we're finding the slope of our original function. So if I'm finding the second derivative, I'm finding the slope of the first derivative. If I'm finding the third derivative, I'm finding the slope of the second derivative. If I'm finding the fourth derivative, because it's the derivative of the third derivative, I'm finding the slope of the third derivative. Okay? So it's all still just about finding slopes. It's just about finding slopes of the function before it, if that makes sense. Okay? So let's try to find some higher order derivatives. In this case, we're going to find the first 4 derivatives of f of x. And luckily, differentiating here will be pretty simple because this is power rule. So let's find f prime of x, our first derivative. So that's going to be a 10x to the fourth, and then a 12x to the third. There's our first derivative. There's the slope of our function. Now let's find the second derivative, which would be the slope of the first derivative. So let's take the derivative of the first derivative. That would be a 40x to the third plus a 36x to the second. And now we'll take the third derivative, which will be the derivative of the second derivative, so the slope of the second derivative. That's 120x to the second and 72x to the first. And then finally the fourth derivative, again the derivative of the third derivative, or the slope of the third derivative, which would be 240x to the first and then 72. So there it is, first 4 derivatives, and when it's a polynomial function, that's all multiplied out for us, no big deal. Okay, now here we're looking for the third derivative, but we don't have a polynomial that's all multiplied out. This one is in factored form. So we have a couple of options. One option would be to go ahead and multiply this out so that it looks like our previous problem and then differentiate. Or, since we already did one that way, we could apply our differentiation rules. In this case, the product rule. Now we've looked at products with or looked at functions with a product of 2 functions. Now we have a product of 3. So let's pretend this wasn't here. If we called this f and g, we know that our derivative would be f prime g plus fg prime. If we have 3 products, and really any number of products, we're just going to make, instead of 2 products, 2 derivatives, this would be 3 products, 3 derivatives. Or instead of the sum of 2 products and 2 derivatives, this would be the sum of 3 products and 3 derivatives. So let's call this f, g, and h. The derivative, first derivative for y, would be f prime g h plus f g prime h plus f g h prime. So it's the sum of 3 products, 3 derivatives. So it's f, g, and h every single time. It's just the derivative of f and then g and then h. Okay, so same product rule, just now with multiple. And if we had 4 functions, then we would have a 4th product in there and a 4th derivative in there. Okay, so let's go ahead and find our derivatives. So y prime. First derivative, f prime. Well, the derivative of f would just be 1. And then g is x minus 6, and h is x plus 5, plus f is x plus 2, g prime is 1, and h is x plus 5, plus f is x plus 2, g is x minus 6, and I should have known to write smaller. I need just a smidge more space. Okay, and then h prime, again, going to be 1. Now, when we go to find the next derivative, I don't want to use my product rule once, twice, and then 3 times if I don't have to. Because multiplying out binomials is pretty easy for me, I would probably at this point go ahead and find the products and then differentiate using the power rule. So I could have multiplied all this out in the beginning and done that. I'm going to go ahead and multiply out here. You have options, so whatever is jumping out at you, that's probably going to be the best thing to do. So here, I'm going to have an x squared, 5x and negative 1x, and negative 6x makes negative 1x, and then I have a minus 30 plus an x squared, 5x and 2x makes 7x, and then 2 and 5 makes 10, and then another x squared, negative 6 and positive 2 makes negative 4x, and then a minus 12. So our first derivative ends up being an x squared, and x squared makes 3x squared, negative x, positive 7x, that's 6, and then 6 minus 4 makes 2 x's, and then finally here, negative 30, positive 10 is negative 20 and negative 12 makes negative 32 for our constant. Alright, so there's our first derivative, and now that I've got that all multiplied out and simplified, finding the second and thirds should be easy. So the second derivative, using my power rule, that's going to be a 6x plus 2, and now my third derivative, nice and easy, is just going to be a 6. And there you have it. There's our third derivative, okay? And you can see the degree of those exponents decreasing every time we differentiate, so it will be possible for our derivatives to be constants or eventually zeros. All right. So now that we have the concept, right, of higher order derivatives, just derivatives of derivatives, let's look at some applications. One of them would be applications to motion, or some things that we might see in like a physics class. So if we were to represent a moving object, an object in motion, like you have a ball that gets thrown upward, or a car, stopped at a light and then the light turns green and the car starts to move, or you're walking, any kind of motion, okay? There are 3 basic ways we describe the motion. So there's the position, like you're a car, you're at a light, and your light turns green, after 10 seconds, how far away are you? After an hour, how far away are you? What's the distance that you have traveled, or the position or distance you are from where you started? So we can use a position function to determine the object or the person's whatever distance from some initial point with respect to time. So if your position function, you input a time and the output is the distance you are from where you started, okay? If we were to find the rate of change in our position with respect to time, then we're talking about velocity. So in our position, again, you input a time and you figure out the distance you are. If I want the rate of change in that distance over time, it's like, oh, I've gone, 10 feet in 2 seconds, or I've gone 50 miles in 3 hours. That rate of change in the distance over time, again, that's velocity. And if we want to know the rate and change in the velocity with respect to time, so how fast is my velocity increasing or is my velocity decreasing, that's acceleration or possibly deceleration. So we can represent the rate of change in velocity with an acceleration function. Okay, and just to be clear with this word velocity, you might be thinking speed. It's the same thing, basically, except speed is always positive, and when we make calculations here, we may end up with a negative velocity or a positive velocity, but it's really just directional, because the velocity is the slope of the position function, right? The rate of change in the position. Position could be positive if we're moving, in a positive direction from our initial point, or if we go in a negative direction from our original, or farther away from where we started in a different direction, we could have a negative velocity. So velocity is positive when we're moving one way from our initial point, and negative if we're going the other way from our initial point. So that's really just directional. And then acceleration could be positive or negative as well, because we could be increasing our velocity or decreasing our velocity. Hopefully that makes sense. So A position function is always going to be in this format. Well, I've used the variable p here, but you could see this replaced by another variable, so I used p for position, but it could be h for a height or d for distance or something like that. But you'll always have negative 16 times your time squared here. A second term with your v sub 0 times time, v sub 0 just meaning your initial velocity. So like if you throw a ball, maybe you throw it with some initial velocity, but if you're stopped at a stoplight, then your initial velocity is going to be 0, so that might not be there. And then p of 0, just your initial position, like where are you starting? Are you starting at a point of 0? Are you starting 150 feet off the ground? What's your initial starting point? All right. If we want the rate of change in the position, again, rate of change, that's slope. That's going to be our velocity. So if I want the slope of the position, if I want the velocity, I take the derivative of the position function. And then if I want the rate of change in velocity or acceleration, I want the slope of the velocity, the rate of change of velocity. So that's the second derivative. All right, so these are, again, applications of higher order derivatives. So just as a sample, if my input is time, obviously, into all of these functions, right? We're inputting a time. But my output in my first function would be some distance. So like maybe your output here is feet. And then the rate of change of that distance with respect to time would be, again, velocity. This would be like maybe how many feet you travel per second. And then the acceleration is the rate of change in the velocity. So that's how many feet per second are you traveling. Like per second, what is the rate of change in that velocity? Okay, so that's what our output sort of will look like. Input's always time. So here's an example. We're going to write all three of these functions and then make a calculation. So a ball is thrown upward from the top of a 160-foot cliff with an initial velocity of 48 feet per second. We're going to find the height, velocity, and acceleration at 4 seconds. So first, let's write a height function. That's our position is height this time. So we're going to write a function that's h of t, and we could have used p, but I'm just going to choose h for height. It will always have a negative 16t squared plus v sub t, so our initial velocity is 48. That gets multiplied by t. And then we're going to add on our p sub 0, that's our initial position. In this case, that's 160 feet at the top of the cliff. So there's our function for position. And I should have said that. All right, so we have position, and then we're going to have velocity, and then we're going to have acceleration, which I'm going to abbreviate because I don't want to write that out. All right, so we have our position function just based on the given information. If I want the velocity function, that's just the first derivative of the position function. So that's going to be a negative 32t plus 48. And then if I want the acceleration function, that's just the second derivative, so the derivative of the first derivative, which would just be a negative 32. All right, so we've done it. Now we want to find each of these things at 4 seconds. So at 4 seconds, what's the distance that we've moved? How fast have we moved? And how fast have we accelerated? So at 4, right, now we got to plug 4 into each of these. So h of 4 would be negative 16 times 4 squared plus 48 times 4 plus 160. And so h of 4 is going to equal, let's find out. I am not trying to do this in my head. So 4 squared plus 48 times 4, and then plus 160 is 96. 96 feet. Okay, so at 4 seconds, this ball is at a height of 96 feet. So it started at 160. I'm imagining it went up because the ball was thrown upward, right? Ball goes up and then it comes back down. So at this point, it's lower than where it started. It's at 96 feet in height. All right, so now we're going to find h prime of 4. Let's find the velocity at 4 seconds. So negative 32 times 4 plus 48. Negative 32 times 4 plus 48 is going to be a negative, did I do that right? Negative 80. So h prime of 4 is a negative 80 and that's feet per second. I feel like, I don't know. -32. Sorry, just don't trust what I just did. Yep, okay, so -80. So this is traveling at -80 feet per second. What does that mean? So if our velocity, remember, velocity is the slope of the position. If the slope is negative, that means that the original was decreasing, right? So decreasing there, put a negative slope for our velocity. So position is decreasing, that means it's heading down. Remember, that's directional. And then the last one, h double prime of for our acceleration at 4 seconds. Well, there isn't anywhere to plug in a t. It's just going to be a constant, -32 feet per second squared. So what does it mean for the acceleration to be negative? It means that the velocity was decreasing. So if the velocity is decreasing, acceleration is negative, that means we're slowing down. And let's go ahead and highlight. Those are the 4 answers there. All right, so again, that's just one application of finding higher order derivatives. Another application deals with something we call concavity and inflection points. So maybe you've talked about concavity in a college algebra class. If not, that's okay. It's a pretty basic concept. It's basically referring to the direction of openness. The direction of openness. When we're talking about the concavity of a function, is which direction does it open? So if it's concave up, it opens up. And if it's concave down, it opens down. And there's more formal definition, but I think that straightforward, less formal definition is hopefully sufficient. So here, for example, would be a portion of graph that is concave down, and then here would be a portion of graph that is concave up, right? It's like a piece of a parabola there, that little, in that neighborhood, it looks parabolic. It's opening down versus opening up. So concave down is that yellow one I highlighted, concave up is that green one. Okay? Now, if we're talking about higher order derivatives, what does this have to do with that, or how do we find these things? Let's talk about the behavior. So if our function is concave up, let's focus on this green one here. What is happening to our derivative? That means what is happening to our slope. So let's say I was finding the slope here. The slope, like at this point right here, that slope, I don't know what it is, but it's pretty steep. Let's just pretend, okay, it's like a -2. Well, at this point down here, our slope is still negative, but not quite as steep as the previous one. So maybe it's like a -1. And then if I go here to this turning point, I know the slope here is going to be a 0. If I go to the slope on this side, it's the same as the slope on the other side, but it's positive. And then the same thing here, the slope is the same as the other side, but it's going to be positive. So if my slope goes from -2 to -1 to 0 to 1 to 2, and those are completely made up numbers, but what's happening is that those slopes are increasing. Okay, so if my graph is concave up, it means that my derivative, my slope, is increasing. My first derivative is increasing, right? What about my second derivative? Okay, if my second derivative is the derivative of the first derivative. The second derivative means if I'm looking at an increasing graph, what's happening to the slope of an increasing graph? It's going to be positive. So if my first derivative is increasing, my second derivative is positive, right? The same thing we did before with the other chain of command, right? If we had an original function and we said it was increasing, that meant that the derivative had to be positive, because an increasing meant a positive slope, right? So the slope is positive. So it's the same thing here now. We're saying the first derivative is increasing, which means the second derivative has to be positive, because if it's increasing here, the slope is positive here, this is positive because it represents the slope in that original. Hopefully that makes sense. Okay, then the reverse is happening when our graph is concave down. So if our graph is concave down, again, let's just say the slope I'm looking for right here, let's just say it's +2. Okay, the slope here, not quite as steep, but still positive. Slope here, definitely going to be 0. Slope here is the same as on the other side, but it's negative. The slope here is the same on the other side, but it's going to be, again, negative. So what's happening if my slope goes from 2 to 1 to 0 to -1? It's decreasing. So if my graph is concave down, that means my slope, my first derivative, is decreasing. So if my first derivative is, what did I dot an e? I don't know. If my first derivative is decreasing, means my second derivative has to be negative. If this is decreasing, that means the slope is negative. That means here, right, second derivative is that slope has to be negative. Okay. And then there is a point in this graph, obviously, where our concavity changes. That point where we went from concave down to concave up, that point is called a point of inflection, or an inflection point. Okay, so concavity changes at a point of inflection. And that means a point of inflection, or at that point of inflection, your second derivative is going to change from positive to negative, or vice versa, right? If we're changed from concave up, where we're increasing, or our second derivative is positive, to concave down, where our second derivative is negative, that inflection point is showing us that change, okay? So we have to be able to, just like we found intervals of increasing and decreasing and the relative minimum and maximum that separated those, we want to find where our graph is concave up versus concave down, and possibly these inflection points that separate those. Again, because there are applications of this. Now, anyone could look at a graph and say, okay, I can see it's concave up, I can see it's concave down. You can't always necessarily see these. Those are a little trickier to calculate, but we do have the algebraic work that can get us the answers that the graph would give us, right? And it's a derivative test. So we use the first derivative to find where graphs are increasing versus decreasing, and again, the relative extrema in between. We're going to use a second derivative test in a similar way. If we find the second derivative, the critical numbers of the second derivative, then we can determine where our graph is concave up versus concave down, and where we might have an inflection point. So our second derivative test means find the second derivative, and then find the critical numbers for the second derivative. So critical numbers do the same thing that they did for the first derivative. They make our derivative equal 0 or undefined, but because they're critical numbers for the second derivative, then we want to know where our second derivative is equal to 0, or where our second derivative is undefined. Okay? And then what we do is, just like when we're using our first derivative test, is we test values that are before, between, or after the critical numbers to determine our concavity. If we plug a number into our second derivative and we get something that is greater than 0, that means we get something that is positive. What does that tell us? Well, we just said up here, if our second derivative is positive, our graph is concave up. So if we plug into our second derivative a test value, we get something positive, we know our function's concave up. And if we get something less than 0, which means it's negative, that's going to tell us our graph is concave down. And a change in concavity, right, a change from concave up to down, or positive to negative, means a critical number may be a point of inflection. And I'm going to say maybe because it doesn't have to be. I'm going to show you an example in a little bit. It's sort of a tricky thing. If we're going to identify an inflection point, a change of concavity will definitely occur, but that change in concavity doesn't mean that we have to have an inflection point. It's tricky, and I don't want to get too muddled up in all that, but let me show you an example first, one that's pretty straightforward. And polynomials tend to be that way. So we're going to try to use our second derivative test to find intervals of concavity and possibly inflection points. So for example, here, if I said find the first derivative, we're looking at 4x cubed plus 3x squared minus 6x. And I could find critical numbers of that would lead me to increasing, decreasing, extrema, those things. But I want to go to the second derivative here. So 12x squared plus 6x minus 6. Now, I want to know where my second derivative is equal to 0 or undefined. So find the critical numbers for my second derivative. Now, this isn't going to be undefined any place, but we can find a couple places where it's going to be equal to 0. So let me divide out the 6. We're going to try to solve 2x squared plus x minus 1 equal to 0. And I'm going to factor this thing. Factors of -2 that make 1, or 2 and -1. I'm using bottoms up to factor. If you have some other method for factoring, whatever works for you. But this is going to factor into an x plus 1 and 2x minus 1, which means our solutions are the values of x that make each of these factors equal 0. So -1 is going to be a solution, and positive 1/2 is going to be a solution. Those are our critical numbers. So I'm going to put those on a number line. So I got -1 over here, and I got positive 1/2 over here. Now I need to test values before, between, and after. So I'm going to test a value by plugging it into my second derivative. So find f double prime of something less than -1, like maybe -2. And again, find something between those. So f double prime of between -1 and 0, -1 and 1/2 would be 0. Anything in between is fine. I just like to plug in 0 when I can. And I'm going to find my second derivative at a positive 1. And those are going to tell me, those test values are going to tell me whether my graph is concave up or concave down in those places. So my second derivative was 12, and then I'm going to plug in -2 squared plus 6 times a -2, and then a minus 6 times -2, and then a minus 6. There's my second derivative. When I input 2, I get a 30, which means that's a positive value here. That tells me that this section of graph is concave up. When I input a 0, I shouldn't have to do this because I know these terms are just going to go away, but just so you can see it, I get a -6. So that negative tells me that here my graph is concave down. And then I'm going to input a positive 1. And I'm going to get a positive 12. Again, positive means here my graph is concave up. So I'm changing concavity, and that means that in this polynomial function that the places where I change concavity, the -1 and 1/2, those could be inflection points. So let's go ahead and confirm this by graphing our original function. So we have the original function, x to the 4th. Oh my gosh, fat finger problems. And then a plus x to the 3rd. Oh, I swear. 3rd. There we go. And then minus 3x squared, and then a plus 1. And so we said concave up, then concave down, then concave up. And then if I look at x equals -1, that point right there, a -1, -2, inflection point, yep, that's where we're changing from concave up to concave down. And then x equals 1/2. And just so you can see that point right there on my curve at 1/2, I can see another inflection point again going from concave down to concave up. All right, so everything looks good. Now let's just answer this question. If I gave this to you like in an assignment, I would ask, what are the intervals where this graph is concave up? And you would say it's concave up here and here. So that's going to be from -infinity to -1, and from 1/2 to infinity. If I said, where is it concave down? You're going to say it's concave down in between those other two intervals where it was concave up, so from -1 to 1/2. And if I said, where do you have the inflection points? Well, those inflection points happened at those changes from up to down and down to up. So inflection points happen at x equals -1 and at x equals 1/2. And if you wanted to find the coordinate, you could either use the graph for that or plug those x values into your original function. You would get the corresponding y values. But just the x values would be good enough. So those inflection points happened here where we changed at those critical numbers. All right, so that would be all the information that we're asked to find there. Now, I mentioned this earlier, but I want to point it out with an example. If we have a point of inflection will always indicate a change in concavity. So if we have a point of inflection, again, there has to be a change in that concavity. It indicates that that's happening. But if we have a change in concavity, it doesn't always indicate a point of inflection. For example, with this rational function, and should make sense. These rationals never behave the way that, behave nicely like our polynomial functions do. So in this rational function, we have some changes in concavity. So this portion of graph we would say is concave up, and then we have this portion of graph that is concave down, and then we have this portion of graph that is concave up. So we have two changes in concavity. Okay, concave up to down, and then down to up. So if we did the work that we just did in that previous problem, we would find a couple of critical numbers. We would have a critical number here, because our graph changes from concave up to concave down. So x equals -2, and we would have a critical number here at x equals +2, because again, our graph is concave up, and then down, then it's down, and then up. So we have changes in concavity there. So if we did our second derivative test, just like we did over here, we'd get that number line, and it would show the same three results: concave up, concave down, concave up. But in the polynomial function, those places where we changed were inflection points. But here, these places where we're changing are not inflection points. They are discontinuities in our graph. So if I have an inflection point, again, it's always going to tell me I have a change in concavity, but a change in concavity does not always guarantee or indicate that we have a point of inflection. It could be something else that's breaking up the graph and causing that behavior to change. Okay? So ultimately, we can use this second derivative test to find our intervals of concavity. Those will always be there, right? But the inflection points are not guaranteed by this test. So the inflection points we sort of have to find looking at our graph. If it's a polynomial, it's probably going to be an inflection point, but it's just not always a guarantee. So we want to double check with our graph. Do we have an inflection point changing the concavity, or is there something else? Okay? Hopefully that makes sense. Now, one application of an inflection point comes in economics. An inflection point of a function in an economic application is known as a point of diminishing returns. A point of diminishing returns, because it is a point in which your returns start to decrease. Let me show you with an example here. Here's an example of a revenue function that's graphed here. So you're producing X items, and then your outputs are the revenue in dollars for producing X items. There is an inflection point in this graph. This graph is concave up to some point here, and then it flips to concave down at some point in there. So again, I can't see exactly where it is, but I know there's going to be an inflection point in here somewhere. So the concavity is changing, right? But what's happening in terms of the revenue? So this revenue is increasing. All the way through increasing. It's the rate at which the increase is changing. So I know, again, this is increasing, and this is increasing, so my first derivative would be positive all the way through. But if I look at the rate of change of the increase, my second derivative, the behavior is different. So the rate of change here, like here for example, my slope is some positive number, right, increasing. And here my slope is again a positive number, but it's definitely steeper, so it's higher, and steeper and steeper and steeper. But what happens after, and this is really terrible here, is definitely steeper, so my rate of change in my slope, which my second derivative, again, rate of change of slope, that's my second derivative, it's increasing until I get to this point here where my slope is still positive, but it's not as steep here as it was. Maybe it's kind of the same here. Like here. I'm just having a hard time drawing these tangent lines. My slopes here are going to be flattening out. So before my inflection point, my slope is increasing, and then here my slope is decreasing. So the second derivative is increasing, the second derivative is decreasing, right? That's my concave up versus concave down. So in terms of revenue, it's increasing all the way through, but it doesn't increase as fast after the inflection point. So again, we call this the point of diminishing returns, because you're still getting a return. It's just not as fast as the return before the inflection point, if that makes sense. So the rate of change change in slope decreases. That's the second derivative. Okay, the rate, or in terms of the revenue isn't increasing as quickly, or the increase in revenue actually slows. Let's say it that way. The increase in revenue slows. So the increase in revenue decreases. I don't know, it's a lot of fancy terminology. I'm hoping that makes sense. So if you have an example, an economic example, so maybe you're talking about revenues or profits or costs, you're asked to find the point of diminishing returns. That's just do the work we did up there to find the inflection point, okay? All right, so I think you should be good to go for your assignment. But as always, if you have any questions, need some extra help, then just reach out. Until next time, take care.